like to share how is a differential constructed, which will be useful especially in electromagnetism and differential calculus and calculation of volume surfaces, perhaps things as applying Gauss's law, but more than that, it will be useful for you to start thinking on how are the differentials, how does the infinitesimal calculus works, and how are those functions inside an integral constructed. Okay, let's suppose that I have to understand how to calculate the volume of a sphere. If you try to calculate the volume of a sphere in Cartesian coordinates, which means x, y, z, it'll be pretty hard to calculate that. But well, in any case, you can try with different shapes, but sooner than later you will find that using these coordinates perhaps might not be very practical to find, for example, the volume of any surface who has spherical symmetry. So there is another set of coordinates. Let me find out a pencil. Let me find a pencil here. Okay, I am gonna describe the spherical coordinates here. I have an angle which is called theta, and this angle, this is a radius. Imagine a 3D a radius in a 3D space, and I'm gonna project this radius r to the xy plane, and in the xy plane I'm going to describe here the projection. I have here the x coordinate of the projection, the y coordinate here, the y coordinate of the projection. Okay, you can check that here, and I am going to I have here a row which is the coordinate of r in the xy plane. But and let's check here that I have an angle which is phi. So I have three coordinates which are going to be r, which is this one, the distance to the origin, theta, which is this one, this angle, the angle that this vector makes to the with the z-axis, and phi, the angle of the projection in the xy plane. Because imagine that you are going to rotate this vector around the z-axis, and if you rotate this vector r around the z-axis, you are keeping the theta angle, but you are changing the phi angle. Okay, and if I change r, I am keeping the phi and the r and the theta, but the distance here is changing. So in any point I can describe in any point I can relationate, I can make a description of the space or of the specific point of the position. I can describe such position based in three coordinates, which are theta, phi, and r. So that is the purpose of a system of coordinates, that you be able to describe any location based on the coordinates that you're having and you of course have to describe the whole dimensions of the system of space. For example, I have 3 dimensions here, so I need 3 coordinates. Okay, so I'm gonna write this, the two angles and the radius. Okay, but what if I want to describe the volume of a shape? I have the volume of a shape, and I have to add the differential volumes. But how do I know which is the right expression for those differential volumes? And this is when I'd like to introduce a method that allows us to comprehend better, in a better way, how to understand which and why is the expression of dv in different sets of coordinates. You will find this, you will find a very formal explanation of this. You will find the Jacobian and several very formal ways in which the mathematicians try to explain this, but I will try to teach you a very practical and intuitive way which you can understand this. Okay, so I'm gonna draw the sphere once again here, and I'm gonna ask you to imagine, please, this is a I'm going to have a shield, a tiny shield, but a small portion of the shield, and I'm going to have this. Just imagine a shield like this one. Okay, you're going to imagine that this sphere, that you're going to have just one layer of the sphere, and also that we are going to take this part of the sphere. This part of the sphere has a surface, which is what you can imagine in 3D. Please imagine that you have something like this. You have something like this. Uh, this surface is going to be like this one. You have something like this, and you are going to project this. You are going to have this also, which is this the 3D. Just imagine that you are advancing here in this axis perpendicular to the paper, and also you are going to have to grasp all the volume of this, and you are going to have also the very same with this other surface, with the layer. So you are going to have something like not, it's not exactly like a cube, but it's like a 3D, like just imagine that you have a 3D portion here. I I know I drew it very bad, but I just want you to imagine this. Okay, this, if you project this in the xy axis here, if you project the arch of such surface in the xy axis, you are going to need to use the phi and the rho. So how much line or how much length do you need to describe this projection? You will need, and you know that this distance is described by rho multiplied by phi. This is a distance which you already know in 2 dimensions. Why do you know that? Because if you have in 2 dimensions, you have a circle and you have your radius are rho, and you take a phi angle of 2p, you know that the whole distance of this is going to have a length of rho multiplied by 2p. So if you grab an angle phi here, then you are going to need only um, an expression, a different expression, which is rho multiplied by phi. How do you know that? Because if I take 2p as an angle, and this means that I am going to have rho multiplied by 2p as the circumference or the perimeter of the whole circle, then if I take phi, it is going to be just a very simple rule, arithmetic rule, that we are going to have phi multiplied by rho multiplied by 2p divided by 2p, so I have only rho multiplied by phi. So this is the expression of any arch like this one, the length of any arch like this one. So here I'm going to have something like rho multiplied by phi, which is going to be this base, But how much distance do we have here? Here I have differential of rho, because it is an infinitesimal change in rho. So now I have the base of this rectangle, this base. Now I have this base. So I'm going to have right here differential of rho. And now let's imagine that we are going to look this. Let's imagine that I have a 3D box here, and I'm going to look at it here, and just remember that the radius, this is the r radius, this is the polar axis, and I have a radius which either lays down or stands here, or lifts, or is lifted here, and it spans all this arch. So I'm going to think in all the arch, the arch here, or better, it will be something like the arch that it forms here. If you imagine that I have this, something like this, okay, and I have once again the box, but it is not a box with a rectangular shape. It has arches. It has arches because its sizes are made of arches. It has some arches as its walls, so it's not in a rectangular way. It's not straight as if it would be some rectangular coordinates. Those are not straight. Those are curved surfaces and curved lines. Okay, so I have curved lines here. Okay, so if you imagine how much is the height of that, you are going to understand that the height is based on this arch also, and this arch also is once again r multiplied by theta, once again by theta. This is r multiplied by theta, and this is, and in the projection I have rho multiplied by phi. So I need here the rho, the r, the r multiplied by the change by the, but this is not going to be phi, because this is only a change in phi. I have here not phi but differential of phi. The differential of phi, which is rho, this whole rho, this is a rho multiplied by only the change in phi. I had here rho multiplied by phi, but if I have only here a differential of phi, I will only have rho multiplied by the differential of phi. Yes, if I have a finite rho, well, I'm going to have a finite phi. I'm going to have rho multiplied by phi. But if I have an infinitesimal quantity or amount of phi, I'm going to have the differential of phi, so it will be rho multiplied by differential of phi. Therefore, I need to correct this here, rho multiplied by differential of phi. Let me write that here once again. Rho multiplied by differential of phi multiplied by differential of rho multiplied by differential of rho. And now I'm going to do the same with this arc, which will be r multiplied by differential of theta. So it will be here rho multiplied by differential of theta. But what is rho? Rho is the projection of rho here is this one is the projection of r in the xy plane. So rho in this position will be r multiplied by sine of theta, which will give us the projection of r in this coordinate. Okay, so rho will be r sine of theta, and I'm going to write the rest. Differential of phi, differential of rho, and this r will be here. This r multiplies with this r, so I will have r squared, and differential of theta. So if you check this expression will be exactly the same that you have when you are introducing yourself to spherical coordinates, and this is the expression for the differential of volume in spherical coordinates. Moreover, if I make this integration here, you already know, perhaps you already know that, but I'm going to repeat it for you. If I integrate here, I need to make an integration. How much does the theta change? This theta starts here in theta equal to 0, and if I move the radius until here, we will have theta equal to p halves, 90 degrees. And if I continue rotating the radius until the opposite direction, I am going to have the theta is equal to p, or 108 degrees. I want, if I continue rotating, such further rotation is going to be described by changing phi. So I only need that theta changes from 0 to p, and phi can change from 0 to 2p, and the radius r can change from 0 to, for example, the radius r uppercase of the sphere. So if I integrate here, the volume of a sphere is going to be the sum of each differential of volume, the whole sum of all the in the whole sphere, the complete sphere. But I'm going to calculate the volume using these coordinates. So I need to remember that I have from 0 to p a changing theta. So I have to sum those differentials which have theta in as one of the factors, and theta changes from 0 to p. I am going to sum from 0 to 2p in the phi coordinate, and this expression will be multiplied, or will have a factor of differential of phi. And I'm going to need also the r coordinate, which will be from 0 to r uppercase. Don't confuse this r uppercase with the changing coordinate, which is going to be r lowercase. And the rest of that will be r squared sine of theta. Okay. This differential represents the differential of volume. Okay. So in phi, I will only have phi can be extracted from here. I can do this differently. If I am going to integrate only in r, then I'm going to notice that all these coordinates are independent coordinates. So I can start integrating that. I'm going to begin with the most internal integral that I have here. So integral of r squared multiplied by a constant is going to be r cubed divided by 3. And I still have the other integrals. This is going to be d theta and d phi. Okay. And now I'm going to integrate further. I'm sorry, I missed that this is changing from 0 to r uppercase. Okay. And now that I think of it, I could have changed already the r multiplied by this r, and the 0 as r is a factor of this other term will be 0. Okay, I'm going to fix that right now, and I can take this expression out of the integral. So I will have, I'm sorry, I forgot the sign. I forgot the sign of theta. Allow me to put it here. Sine of theta. Okay, this will be equal to integral. Well, okay, as this doesn't change in theta nor in phi, this doesn't affect those other expressions of the integral, so I'm going to take this out. So I will have r cube divided by 3 multiplied by which is a factor of 0 to p multiplied by this internal integral which goes from 0 to 2p in phi. As phi is independent of the theta, then I'm going to only integrate integral of the phi, integral of 1 the phi. So it is going to be precisely phi integrated in 0 to 2p, and this is going to be by the differential of theta by the differential of by sine of theta differential of theta. So I only have 1/4. So I only have one expression left here. Allow me to grab some paper here so I can end this exercise with you. So I have r cube divided by 3 multiplied by, let's continue this, multiplied by this expression in phi. I can take it out because phi doesn't change with theta, so I'm going to have phi between phi integrated in 0 and 2p. Well, the part of 0 goes because it is 0, so I am going to have only 2p, so I'm going to write 2p here, and this multiplies the rest of the integral. The rest of the integral is going to be 0 to p sine of theta d theta. But what is the integral of sine of theta d theta? The integral of sine is minus cosine of theta, integrated between 0 and p. But what is this integral? It is minus cosine of p minus cosine of 0. But what is that? It is minus cosine of p is minus 1 and cosine of 0 is 1. So I have minus 1 minus 1. So I have minus 2. So I have plus 2. Okay. So this integral, which is all of this becomes 2. So I can rewrite all of this like r cube divided by 3 multiplied by 2p multiplied by 2. So I'm going to have here 4p divided by 3, 4p divided by 3 r cube. Okay, and this is the pretty well known formula for the volume of a sphere.